You may not have heard of this plane. It's the experimental bomber, 70 Valkyrie, a supersonic strategic nuclear bomber capable of reaching just over 3 times the speed of sound, or just over Mach 3. It was capable of intercontinental flights and was practically unreachable by any fighter or missile of its time. It was an aircraft like no other and far ahead of its time. During supersonic flights, its wings folded downward to exploit a newly discovered phenomenon. 6 massive engines powered it. It had canards, which are these smaller wings at the front that solved a terrible aerodynamic problem. The front part of the nose would lower. Yes, just like on the Concorde, though the Concorde arrived 5 years later. This was all made in the 50s, well before the Concorde or Strategic Reconnaissance 71. The XB-70 Valkyrie was developed solely to take off from the United States, to reach 3 times the speed of sound so that no fighter or missile could catch it, fly to the Soviet Union and drop its deadly payload, a thermonuclear atomic bomb, return to the United States and land safely. But even before the Americans could carry out this ambitious plan, the XB-70 became involved in a series of tragedies. In the mid-1950s, tensions between the United States and the Soviet Union kept rising, with both countries possessing increasingly destructive nuclear weapons. However, the only thing that both lacked was a way to deliver these apocalyptic weapons to each other's doorstep. At that time, intercontinental ballistic missiles were still in early development, and no fighter jet had enough range to travel long distances. And the bombers of that time flew too slowly, making them easy targets for missiles. And it was with the aim of solving this problem that the idea for the XB-70 Valkyrie came about, proposed by North American Aviation. To make their project stand out from the competition, North American explored a concept from a little-known 1956 report proposed by 2 wind tunnel experts from National Advisory Committee for Aeronautics. This is now called compression lift. When flying above the speed of sound, shock waves are formed. They come from places like the plane's nose, wing edges, and engine air intakes. These waves tend to move away from the plane, but if they could be directed and trapped by a sort of tunnel under the wings, these shock waves would theoretically increase the plane's lift. The engineers at North American wanted to apply this principle to the XB-70. That's why the XB-70 Valkyrie's wings fold downward, forming a tunnel during supersonic flight that traps shock waves and boosts lift. During takeoff and landing, the variable geometry wings are fully extended. During low-speed supersonic flights, they are slightly folded downward at 25 degrees. During the high-speed supersonic flights, they are fully folded downward at 65 degrees, creating the iconic tunnel. But folding wings alone weren't enough for a bomber to safely enter and exit the feared Soviet Union. A missile barrage awaits its target. That's why the XB-70 would have 6 General Electric turbojet engines with 11-stage compressors and 2-stage turbines. YJ-93G33. With afterburner using jet propellant 6 fuel, specially developed for this aircraft with a high ignition and low freezing point, each engine weighed 2 tons, 368 kilograms, and produced 128 kilonewtons of thrust. These engines are housed in individual compartments, but how can 6 engines propel it to a supersonic speed of just over 3 times the speed of sound? These engines would need really a lot of air to work properly. This air absolutely cannot enter the engines at supersonic speeds because it would cause the engines to immediately shut down. That's why 2 air intakes were designed, one on each side, with variable geometries, to prevent the supersonic shock wave generated during supersonic flights from reaching the engines. Each intake supplied air to 3 engines. Much of the engineering in the experimental bomber 70 project is found in these air intakes. These engines reach their maximum efficiency in supersonic flight and were designed to keep the afterburners on for most of the flight time. Flying at triple the speed of sound creates intense air friction, significantly heating the fuselage and damaging the aluminum. That's what many aircraft are made of. That's why the experimental bomber was mostly made of stainless steel, as well as composite materials known in English as honeycomb and titanium. These materials withstood the high temperatures of supersonic flight, reaching up to 360 degrees Celsius. Like the Tupolev 144, the experimental bomber, 70 also had canards, which are front wings on the aircraft. As an aircraft exceeds the speed of sound, it goes faster. The aircraft's center of lift, an imaginary point above the wing where most lift is concentrated, begins to shift backward. This creates what is called a heavy nose. Basically, the aircraft tends to lower its nose due to this shift. Some designs use canards, front wings that generate lift, to address this. It's also a way to avoid adding flaps to delta wing aircraft. Sometimes gimbal mechanisms on engines cancel out this tendency. On the Concorde, it was eliminated by moving fuel through several fuel tanks spread throughout the aircraft as it accelerated in supersonic flight. And that was done by someone, a flight engineer. And those canards on the experimental bomber, 70 could be trimmed during flight, changing their angle. Delta wings, specially designed for supersonic flight above Mach 3. At the rear of the delta wings, there is a series of elevons, a combination of elevators and ailerons responsible for roll movements and for raising and lowering the nose. They were hydraulically controlled and could move individually or simultaneously, depending on the setting. Along with them, it had two vertical stabilizers that moved as a whole. Visually, the most impressive feature of the experimental bomber, 70 Valkyrie, was its landing gear mechanism extending and retracting. The wheels had a mechanism that set them vertically and rotated them 90 degrees to face the plane's center, and only after that were they stored in the landing gear compartment, one of the most complex landing gear retraction mechanisms ever developed. And this whole process of lowering or retracting the landing gear took about 20 seconds, and the wheels were silver, not black. That's because Goodrich developed a special component that was resistant to high temperatures, and they embedded it in the body and on the outside of the tires, so they could withstand temperatures of up to 182 degrees Celsius. And these tires were cooled from the inside through small tubes that circulated a chemical mixture. The cockpit was very analog and accommodated a crew of 4, pilot, co-pilot, and 2 officers responsible for specific mission-related functions. The seats for the entire crew became a kind of individual pressurized survival capsule, which would automatically close in emergencies, such as depressurization. And they were specially designed for ejection during flight at high altitude and high speeds. When the first prototype was ready, in 1964 ground testing began. But even in the first tests, several technical problems occurred. And even taxiing the plane down the runway was a difficult task, simply because the pilot was 20 meters ahead of the nose gear. The first flight occurred on September the 21st, to the delight of its large design team. However, the celebration was short-lived due to a hydraulic fluid leak that kept the landing gear from retracting. Shortly after, one of the engines reached 108% power, forcing a shutdown. As the prototype was preparing to land, a problem occurred with the brakes, causing them to remain permanently engaged, which started a fire. As soon as the prototype landed, the wheels were severely damaged, but the prototype survived. All these problems and a series of repairs were made. 2 weeks later, on October 12th of that year, the prototype broke the sound barrier for the first time, but without exceeding it by much, staying just slightly above it. The prototype was repeatedly slowed and then accelerated back to supersonic flight. However, much of the plane's paint began peeling. It looked like the plane had just returned from an atmospheric re-entry. Despite that, the plane was brought in for a safe landing. The paint was too thick, which caused it to strip off during the flight. On its 12th flight, the plane reached Mach 2.6 or 2.6 times the speed of sound. The leading edge of the wings came off and was sucked into the engine ducts, damaging engines 3, 4, 5, and 6. The pilots landed safely, but all affected engines needed replacement. On October 14th, the plane was finally ready for Mach 3. But after just 2 minutes of the plane being put in that condition, a large piece of the wingtip was torn off, forcing the pilots to make an emergency landing again. It seemed that as soon as some problems were solved, several others would arise. Because of these problems, the first prototype's top speed was Mach 2.5. Meanwhile, lessons learned during the construction and testing phase of the first prototype were used to improve the construction of the second prototype, which was already being built, with emphasis on reducing manufacturing time and adding 5 more degrees to the wing sweep to increase the aircraft's directional stability. But doubts began to arise about whether the bomber would ever be able to achieve and fulfill its objective. To make things worse, the Soviet Union shot down a supposedly untouchable U-2 spy plane with a missile at 24 kilometers altitude. Soviet missiles had become more capable than previously thought. Meanwhile, American intercontinental ballistic missiles became more capable and reliable, able to launch between countries without risking lives. This left the future of the experimental bomber 70 uncertain. There were plans to make it a platform for testing other spacecraft, aircraft, or supersonic missiles. There were proposals to turn it into a supersonic passenger transport plane, and this was one of the most promising ideas. And with the project's funding cuts, it was reduced to just 2 aircraft. But since many millions had already been spent, the project continued. In 1966, National Aeronautics and Space Administration and the Air Force began testing with just 2 prototypes. And with that, valuable data about supersonic flight was obtained, with the second prototype proving to be more capable than the first. On May 19th, the second prototype reached speeds well above Mach 3 for more than 30 minutes, demonstrating its enormous potential. On June 8, 1966, the second prototype, with its wings slightly raised, set out for another test flight. And then it would join other planes in formation for filming purposes. But after a few minutes flying in formation, one of the planes on the right side, which was closest to the experimental bomber 70, got too close and ended up colliding. After the collision, the plane went over the experimental bomber 70 and partly tore off both vertical stabilizers. The experimental bomber 70 Valkyrie flew perfectly for 16 seconds before entering an uncontrollable spin. In a matter of seconds, 2 pilots and a billion-dollar prototype were lost. It measures 56.6 meters, 32 meters from wingtip to wingtip, just over 9 meters tall at the tail, weighs 93 tons empty and 242.5 tons when loaded. 6 afterburning engines pushed it to a top speed of 3,300 kilometers per hour. It had a maximum range of 7,900 kilometers and flew at 23,600 meters, or 77,400 feet, far above the reach of any interceptor or missile of that time. Mid-flight folding variable geometry wings utilized compression lift, a newly discovered principle that increased stability, reduced drag, and created a tunnel in supersonic flight, trapping shock waves and increasing the plane's lift by up to 30%, allowing it to have a lower angle of attack during cruise at supersonic speeds, canards to solve the lift problem in supersonic flight, 2 vertical stabilizers shorter than originally planned, thanks to the increased stability provided by compression lift. A retractable nose enhances pilot visibility during ground taxiing. Combustible materials, landing gear, technical technologies, and pioneering principles, specially developed for this aircraft. The engineers had outdone themselves and surpassed all limits to create an aircraft far ahead of its time, which seemed to have come straight from the future. And all of this was conceived, created, tested, and perfected in the 1950s, when there weren't even computers to simulate fluid dynamics in detail. Testing different wing profiles and behaviors in supersonic flight, testing rare aerodynamic phenomena that could occur in supersonic flights close to Mach 3. But despite all that, they succeeded and created a truly revolutionary aircraft. In the end, the experimental bomber never served its purpose, becoming obsolete before construction finished, due to the emergence of much more advanced Soviet missiles, which could reach the high altitudes where the experimental bomber 70 would fly. But not everything was a failure. A lot was learned, and from all the knowledge gained during the development phase, construction, testing, and supersonic flights developed the B-1B Lancer bomber, and especially the Strategic Reconnaissance 71, the world's fastest plane.